Welcome back to LearningHub. In the previous video, we explored the mathematical foundations of machine learning. We talked about scalars, vectors, matrices, tensors, and how data gets represented in matrix form. But today, we're taking that understanding one step further into the world of matrix transformations, where math starts to move, rotate, and reshape data in fascinating ways. First of all, we'll start with part 1, what matrix multiplication means geometrically. So matrix multiplication isn't just about crunching numbers, it's about transforming space. Imagine you have a bunch of 2D points on a plane. When you multiply those points by a matrix, you're not just doing math, you're applying transformation. So the transformation could mean rotating the points, stretching them, shrinking them, or even tilting the whole space into a new position. So each matrix acts like a lens that reshapes how vectors look into space. So in simple words, we can say that multiplying a matrix by a vector changes how the vector looks without necessarily changing what it represents. That's why the matrix multiplication is such a big deal in ML. It transforms data into new forms and models that models can learn from. Let's make this transformation idea more concrete. There are three basic transformations you'll often see: rotation, scaling, and shearing. First of all, we start with rotation. When you rotate a vector, you're changing its direction but not its length. So the rotation matrix looks like this 2D matrix you see here. If you apply this to a vector, it spins that vector around the origin by an angle theta. For example, rotating 1, 0 by 90 degree gives you 0, 1. It's like turning a clock hand, same size, new direction. Next is scaling, which stretches or shrinks your vector. The scaling matrix, as shown here, you can see that Sx and Sy terms. So Sx and Sy are scale factors along the x and y axis. If both of these are greater than 1, your shape grows larger. If they are between 0 and 1, your shape shrinks. Scaling affects the magnitude but not the direction or the angle of the vector. And finally, we have shear. Shearing slants the shape. Imagine pushing the top of the square sideways to become so that it becomes a parallelogram. A shear matrix looks like this, as shown here. This is for the horizontal shear and this is for the vertical shear, where K here is the shearing factor. Now shear changes shape but keeps one set of sides parallel, which is a beautiful geometrical twist. Next, here is something that often surprises beginners. Whenever we perform some matrix mathematics, order matters. So in regular arithmetic, 2 multiplied by 3 gives you the same result as 3 multiplied by 2. But as we talked earlier, multiplication of matrix A and B is not the same as multiplication of matrix B and A most of the time. And sometimes one of them isn't even possible to compute. Suppose we have a matrix A that is of shape 2 into 3 and matrix B is of shape 3 into 2. Multiplying A into B gives you a matrix 2 into 2 shape. But multiplying B into A gives you a 3 by 3 matrix. So the result, even if both are valid, represents completely different transformations here. So when we multiply matrices, we're applying transformations in sequence. Think of it like performing actions onto a vector. So if you do B times Ax, that means you first apply A and then you apply B to X, right? But if you flip it to A times Bx, then you're applying them in the opposite order, and that changes the outcome entirely. So in ML term, this order defines how data flow through transformations. For instance, in linear regression, we do y hat equals to x into beta. It works perfectly, but if we try to reverse this into beta into x, that doesn't make sense. The dimensions simply don't align. So to sum it up, matrix multiplication represents geometric transformation. Rotation changes direction, scaling changes size, and shear changes shape. And the order of how you apply them changes the entire outcome. And that's the beauty of linear algebra. It gives us the language to describe transformations in data, geometry, and even machine learning models. So this was another episode into our Maths for Machine Learning series here on LearningHub. If you're enjoying this journey into math behind ML, don't forget to like the video, subscribe, and hit that bell icon. And I'll see you in the next one.